So today we're going to learn how to determine how many significant figures are in a measurement. So when you're in chemistry class, a lot of times you are measuring lengths, masses, volumes, so on and so forth, using measurement tools. When you have a measurement tool, there is a concept called significant figures that is attached to every single measurement tool. Now, I want you to notice on the wall there's a poster with all my significant figure rules there. So you're not going to have to memorize the significant figure rules, but you do have to know how to use them. So in order to indicate how precise our measurement tools are, we're going to use a concept called significant figures. Significant figures are the digits that you know for sure and one place that's an estimate. So each measurement tool has what's called calibration marks, where as they are created, they are calibrated, or their measurement is precisely marked on the tool. So you can see I have a picture of two different measurement tools that have different markings on them. The top ruler only has markings every one, let's just say, centimeter. That means that it is not as accurate as the next one, which has markings every centimeter, but then every centimeter is broken up into 10 spaces. So it's every millimeter. So the first ruler is not as precise or accurate as the second ruler, which is more precise or accurate. So the first ruler, I can look at that and say, I can read right off the measurement the tool that it's somewhere between 8 and 9 centimeters. I'm going to say 8.9. That's as far as I can read. That's as accurate as I can go. The second measurement tool, I can read 8.9 right off the measurement tool, and then I'm going to estimate it's halfway between. So I'm going to record my measurement as 8.95. So the second measurement tool actually has one extra significant figure. It is more precise. All right, so here's our rules. Our rules for counting significant figures. Non-zero digits are always significant. So non-zero is any other digit besides 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9. The number 3, 4, 5, 6 has 4 significant figures. Now let's go to our rules for zeros. Zeros that come in the beginning of a number are never significant. They're only placeholder zeros. So if you see a number that starts with 0, those zeros aren't significant. So the number 0.0486 has 3 significant figures, and those are called leading zeros. The next kind of zero is called a captive zero. Captive zeros are numbers that are trapped between two non-zero digits. So a zero that is trapped between two non-zero digits is always significant. So 16.07 would have 4 significant figures. Trailing zeros are zeros that come at the end of a number. They're the last digits in a number. Trailing zeros are only significant if there's a decimal point in the number. It doesn't matter where the decimal point is. You simply ask yourself, is there a decimal point anywhere in this number? If the answer is yes, then those zeros are significant. So 9.300 has 4 significant figures. If there is no decimal point in the number, then trailing zeros are not significant. There's a couple special situations that have what's called an unlimited number of significant figures. Counted items. For example, there's 26 students in this classroom. If you get any other number but 26, you're simply wrong. So that's called a counted digit. Counted items are always unlimited significant figures. So if you're not using a measurement tool, if you're just counting things, it's unlimited. The other thing is reference values. So exactly defined quantities like 60 minutes equals 1 hour, that's a reference value. Those are not going to be counted when we're determining significant figures. They're unlimited number of significant figures. So let's summarize that. Leading zeros are never significant. 0.00068 has 2 significant figures. Captive zeros are always significant. 100.03 has 5 significant figures. Trailing zeros are only significant if a decimal is present. So 12.300 grams has 5 significant figures, but 12,300 grams with no decimal point has only 3 significant figures. So that's the only thing that can be a little confusing. So always significant are non-zero digits, captive zeros, and trailing zeros with a decimal place. Never significant are leading zeros and trailing zeros without a decimal. The next little piece is scientific notation, which we will be using quite a bit of. The coefficients are significant. All of the digits in the coefficients are significant, but none of the other numbers, not the 10 or the exponent. Let's test ourselves. How many significant figures are in this number? It is 5. The first 2 zeros are captive, the last 0 is trailing, and there is a decimal. They're all significant figures. How many significant figures? It is 4. Those are all significant figures also. Be careful with this one. How many significant figures do you count? You should have counted 5. That last 0 is a trailing 0, and there's no decimal, so it is not significant. How many? Did you get 3? How about this number? Be careful. Those are leading zeros. Leading zeros are never significant. They're only placeholder zeros. How many? Those are trailing zeros with no decimal point. How many? It would be an unlimited amount, because if you had 5 dogs, the only way you wouldn't really measure how many dogs you had, you would count them. So you have to be using a measurement tool in order to have a number of significant figures. So how is this going to be important? Well, in general, a calculated answer cannot be more precise than the least precise measurement from which it was calculated. So kind of like that chain is only as strong as its weakest link. So what happens is we can't just report. You guys know if you type it into your calculator, you're going to get lots and lots and lots of digits, but a lot of those digits don't make sense. So we would have to round them off to the correct number of significant figures. So in order to round, you decide how many significant figures are needed, and then we're going to use our rounding rules we've been using for forever. So if it is less than 5, you drop it. If it's 5 or greater, you increase it by 1. So I know that we've been rounding numbers for forever. So you're going to figure out how many significant figures your answer needs to have, and then you're going to round it to the correct number of significant figures. So in addition and subtraction, the answer should be rounded to the same number of decimal places as the least number of decimal places in the problem. We'll practice this so it'll seem more natural when we get to the problems. Multiplication and division, you're going to round the answer to the same number of significant figures as the least number of significant figures in the problem. So let's see how that helps us. So remember, multiplication is the least precise measurement. So if you look at the problem, you'll determine that 6.38 has 3 significant figures, 2.0 has 2 significant figures. Your calculator is going to give you an answer of 12.76. But because 2.0 only has 2 significant figures, I'm going to round my answer to 2 significant figures. 12.76 is not a logical answer based on our measurement tools that we used. Okay, so let's practice this. If you plug this into your calculator, 3.24 meters times 7.0 meters, the meters tells us we measured it. My calculator says 22.68 meters squared, but because 7.0 has 2, I'm going to round it and report my answer as 23 meters squared. This is division. It's the same type of answer. So 100.0 grams has 4 significant figures. 23.7 centimeters cubed has 3 significant figures. My calculator is going to give me a big long number that doesn't really make sense. Because 23.7 has 3 significant figures, that's what I will round my answer to. I find that people tend to forget that we know how to round numbers and kind of get lazy with that. Try to remember that we need to be careful with our rounding. 0.02 centimeters only has 1 significant figure. 2.371 has 4. But we cannot report our answer in anything more precise than our least precise measurement. So even though my calculator says 0.04742, I would need to round it to 1 significant figure. Two significant figures for this answer. So this last step that's going to be brand new to you is rounding your answer to the correct number of significant figures. Now notice this last problem needs to be rounded to 3 significant figures, but there's 4 digits. Well, how I would do that would be leave a decimal point off, and 5870 has 3 significant figures. This one needs to be rounded to 3 significant figures also. Let's practice addition and subtraction. The number of decimal places in the result equals the number of decimal places in the least precise measurement. So for example, this particular problem has 1 past the decimal, so 1 in the 10th place. So my answer, even though my calculator gives me an answer that is longer, my answer needs to have only 1 digit past the decimal. So this is an addition and subtraction. So in this case, 1 past the decimal. In this case, 1 past the decimal. In this case, we have 2 past the decimal. You're going to make your reported answer match the least precise measurement in the problem. Now, let's be careful here. Notice that each of my measurements in the problem have 3 past the decimal. My calculator only gives me an answer that has 2 past the decimal. I actually have to add a trailing 0 in that particular circumstance. So significant figures in a measurement include all of the digits that are known, plus one or more digit that is estimated. So you're going to read certain digits right off of the measurement tools. Those are called my certain digits. And you're going to add one significant figure that's called my estimated digit. You must report answers in science class in the correct number of significant figures. That is our introduction to significant figures, which we will be using in all of our calculations and all of our answers to all of our problems. Now you just need to practice using those before we get to actual problems.